All right, so before we jump into the meeting, let's look at this month's Python pop quiz brought to you by Mike Driscoll. Now this one is a little bit more intensive than some of the past ones, so we're gonna have to do this one in Visual Studio Code as opposed to a REPL. I suppose I could do a REPL, but it gets a little tricky if we're gonna be changing imports or functions, what have you. Now we've had some suggestions here. Robert had an interesting one talking about undefining the function, deleting at some point, and then also had some.
I mean, yeah, the obvious answer is you just use best practices and you don't override the name of the module, right? That's the obvious answer. But the more interesting answer is there a way that you could if it say in a Jupyter session, if you polluted your namespace by creating this bonehead function name, could you get rid of it?
Right, right. So I guess we can look at all of them real quick. We get a lot of 101 Python 101 types around here. So one of the things you can do in Python when you're importing a library or module is you can give it something of an alias. So you do
Where did the F come from in line 7?
so that is an F string that's formatting um, values based on these like curly brace things. So we have a value that's being passed into number here when that function main is called. And so in the case of number, 8 is being substituted for this value of number. And then so in F strings, you can do function calls and whatever is returned there, as long as it's printable, can be dumped in. There may be some special rules there that a handful, I don't know, I feel like Deanne might know off the hand. Can you
It,
dump an
it
object
helps
in
with
there?
string interpolation, right? The F format string.
Yeah, there's some other ways to do it. But yeah, F string is released, what was that, 3 point something, 8? I don't know. But did that
2.6.
6? Okay.
Yeah. You
3 points.
in modern Python, you end up typing that F for the F string so many times you don't even realize you're doing it.
Yeah, exactly. All right, so one solution was to not do the proper thing and instead overwrite the name of the module, because the issue here, oh wait, I'm sorry. Let's back up and let's run this thing. So we get an error here. Attribute error, function object has no attribute square root. So I think we all know that if you're in Python, square root of 9 or something like that, that would give you 3, right? So obviously math, which we imported, has a function called square root. So what happened here? Well, look, going through here, we've defined 2 functions and we called one of them math. Now that's a problem, right? Now we've got a module that we're hoping brings a bunch of tools to the table, and then we're creating a function. So we're basically overriding the math module with some dumb function called math that takes a single parameter and returns what we hope is the square root of that. But unfortunately, we've overridden. So what did we end up with here? If we had a function inside that is called square root or something like that, we'd end up with some sort of recursive problem because we're effectively calling the function or something. So one way was to create an alias for math. So import math as m or something like that. And now that function of square root, we're calling it in the math function. So all we'd have to do there is change the name of that. And I think we have to quit out of our REPL here. So if we run that again, this should work because now the function math is no longer running into the module math because the module math is now referred to as m. So you run that. Oh, there we go. The square root is, as everyone knows, 2.82842727, blah, blah, blah. Like they teach you in school. You gotta memorize that one. But Robert points out that, and James pointed out, why do that? Why not just make a less dumb function name? So instead of doing that, instead of doing an alias, well, let's call this one M instead. Or maybe I'll call this calculate.
Yeah, probably the most important thing is that the final function of main that's really has no relevance to what the problem is, right? It's only just the import statement, and then the way calculate is defined is where the issue is.
Right, bumping into each other in the namespace. So, boom, same thing. Now, you had some funny ones, Robert. You were saying there was something like undefining the.
Yeah. Yeah, you can there are ways that you can delete symbols, right, from the global namespace. So you can define a function, and then you can, I think the correct term is undefined, although it could be delete. Let me see what I put. Yes, delete. So you're deleting the symbol, or you're deleting the label math, right? And now you can turn around and you can re-import math, and then you, in this case, you just skip creating the bogus function, and you just call math.square root directly.
Okay, so where would we put that? Where do we delete math?
So okay, so you've defined a label called math, right? And then right under that, and I mean back at the fully unindented under that, you would just put the command del for delete.
Okay, so here.
Okay, so here, so your function, get rid of the blank space, so you keep all that together, right? And then before where you have def main, type in del math, right? And it even colorizes it for you to show that's a label. And so now you can import math, and now you're back to where you started, right? So, but here, you're calling math.number, which is still screwy, right? Because when you deleted this, you deleted the symbol math that's an override.
Right.
So at this point, what you can do is you can just type in print math.sqrt and just not even fuck with your custom definition, right?
All right,
You
so
just call math.sqrt directly.
Gotcha.
Akshay asks, why can't we simply import the math module inside the math function? That's actually a very good question.
That would still work, right? So that makes no sense, because that would be still in the function scope instead of the global scope. So it's not going to get polluted. And when the interpreter is going to run, and it's just going to say this thing as function, which has been called, and that would be still the local scope for that particular thing. So it would still run.
So yeah, so then the real question is, can imports be scoped, right? So that you can limit that import to a particular function.
Before we move on,
I don't know.
The answer is yes, you can. All right. But you run foul of something else. So the issue that we're getting into with this solution is that we're completely changing the code. So I'm not quite sure if that's within Mike Driscoll's rules.
Yeah, I don't think.
Can we go back?
So I have a very curt and concise reply to that.
and one to which most of us will agree. Okay, we back to square one, Woody?
I have a question. When we define a function in line number 3, and what is the use of the definition again, line number 10? Because we can do the same f function instead of main. We can write print the square root of instead of number. If we define something, can we not do that way as well?
Oh, you're saying like instead of calling main and making that
Yes.
and,
Yeah, print f square root of instead of number. Yeah, number is same and is math. Yeah, math number. Is it not possible? Or
I
if
think
we, yeah,
there's reasons not to, I think.
if we name the math and say calculate, because the math and the module import math is contradicting one each other. So that way,
Yeah. But now if we're just calling print, we now no longer have a value of number. So, you know, what are we doing? Number is equal to 8 or something, as opposed to just passing in a value of 8. I mean, this I think is still gonna have the same issue. Or wait,
Still gonna fail
yeah, but
in the original code.
no, we have to, okay.
If you take out line 4, it will fail.
right.
No,
Yeah.
we have to define like a math. After line 12, we have to define like we did a math. Yeah, main 8 instead of that. If we type math and 8, I think it will work.
Right.
Yeah, so now you're changing the code again by taking out the function at line 3.
Okay.
Yeah.
Yeah. Yeah. It's,
Say
Yeah.
calculate. Say if you put calculate there instead
Yeah,
of
yeah,
math.
okay. So
yeah.
can we
I
go
think-
back to
yeah,
can we go back to the beginning, please, Woody?
Yeah.
Oh, Control Z's a wonderful thing. Control Z, there we go. We can translate from
Use
one
it all
English
the
to
time.
another. Yeah. So the way that Python, oh, he's getting busy here. The way that Python works is that when it first starts, you're in the global scope. So at line 1, you suddenly enter the symbol math, which is referring to the Python standard library called math.
Correct.
Then at line 3, you define, you
User define.
redefine, or that is to say, you change the math symbol so that instead of pointing to the library, it's now pointing to the custom function at line 3. Then we go down to line 7 where we define another function. So finally we end up with a second symbol called main. We go down to line 10, main is called. Now what happens now is we leave the global scope and we go into a local scope, which we will call main. All right, it's the second entry on the stack. And at that point in time, we go through looking at the print statement and we try and call the math function. And that works because math is defined in the global scope. It's not defined in main's local scope, but it is defined in the global scope. And so we go to the function that begins at line 3. And therein lies the problem, because when we hit what is currently line 5, we are talking about ourselves. In the math scope, we're talking about ourselves. And it's not going to happen. So yes, one of the solutions was to put in line 4.
Right.
And what that does is, although math is in the global scope, when we start the function at line 3, we start a new local scope and we can call math there quite independently of the fact that the scope is, if you like, called math. And so that will work in terms of logic. However, it doesn't work in terms of PEP 8 because PEP 8 says, put all your imports at the beginning of your program. Okay. Is there anybody who doesn't understand why this is such a terrible question?
Well, I think it does open up some questions for a less for the 101 crowd. But then also, I'm curious about implementing what James is talking about without going too much longer on this. He says the most indirect way I can think of is with higher order decorator and bytecode transformation / closure and
Oh my
judgment.
goodness. Yeah. The better solution is what Rob said, which is you find the person who coded this function called math at line 3, you take them outside, and perhaps you come back in alone.
There you
And,
go.
and you get rid of that whole function because it's totally unnecessary.
Yeah.
And as suggested before, you modify line 8 and just
Or-
call square root. Why have a function which calls a function and does nothing else? It hasn't added any value.
Or more likely, you come up with all different types of ways to insult the person during code review, right?
Well, that might do something for venting your your situation the way you're thinking, but not so sure that it's a good idea.
Yes, not
Perhaps,
a permanent solution.
yeah.
Actually, a quick question I had was if you have the local import on line 4, you no longer need the line 1, right? I mean, the global import is unnecessary. Is that correct?
Correct,
Yeah.
because it's not used.
Yeah.
The symbol it's overridden as soon as the interpreter gets to line 3. Interpret
Gotcha.
it. Excuse me. It overwrites is the way we think of it, but it adjusts the pointer that previously pointed to the library to now point to a function.
Yep.
And so you're absolutely right. Get rid of line 1 if you're going to do that. But no, I mean, James's solution at the very beginning was the right one. Keep it where it is. Don't confuse us, because anybody who sees the word math is going to assume we're talking about the Python standard library.
Yeah. Something that can totally happen is you can define a variable called sum, right?
That's a common one, isn't it? Yeah.
What?
That's a common one where people get
That's
themselves
a very
into a
common
tangle.
one. So yeah, so I create a variable called sum, and then later on, and it's obviously not right next to it, I try to call the sum built-in function, and it doesn't work.
Right. James, do you think you could concisely walk me through this obscure technique? Types.function type within the decorator. Decorator for which function? The math function?
So there's a couple of different techniques here,
Yeah.
but the way that line 10 works to actually get whatever this math symbol is,
Right.
is an interesting detail of how the Python compiler works. There's only 3 or 4 interesting, 3.5 interesting things that the Python compiler does. One of them is scope determination. So when Python creates that math function, it looks at the body of that math function and looks at all the names that are used there, like number and math, and it tries to figure out, okay, where did these names come from? And it knows that number is a local variable, so it generates a bytecode for that saying load fast, this is a local variable. It doesn't know where math came from because it doesn't see it defined anywhere in its local scope or in its closed over scope. So if it can't figure out where the name came from, it's going to assume that the name is global. This is necessary because you can create things that a function refers to after the function is defined. So you can have a function f on line 1 that calls a function g that isn't defined until line 10. So the parser doesn't know where math came from. It's just going to say it's in the global scope somewhere. It's going to be defined somehow, maybe before, maybe after. What you can do through some very hacky techniques historically and through some other techniques, some recent changes were made to how the CPython interpreter works to allow JITs and things like that to work a little bit better, is you can take the bytecode for that math function and you can swap out the load global reference for a load deref reference to turn it into a closure variable instead, and then swap out the function with a function that has the original math symbol in a closure. That way, the code in the body will look identical, but instead of that being a global lookup, it'll now be a closed over lookup. This probably needs a higher order decorator because you'll need to capture what the state of the global scope is prior to the definition of that function. And so I think unless you use some inspect frame tricks, it's going to be kind of tricky to do that. So probably the safest way for a very unsafe technique would be to use a higher order decorator.
Yeah.
Actually, I had another interesting point. And this is kind of interesting about when we talk about global scope, because a lot of people who have C or C++ experience really think about global scope as being the one global scope that exists for the whole program. That's not really how it works in Python. In Python, all modules have their own global scope. It's really module scope. And if you dig into that Python function object that you have, you can actually see that it refers to its particular global scope. Well, if you had two files, they have different global scopes. In Akshay's version, what he is thinking about doing is saying, oh, this function doesn't refer to the global scope in the file that you have here. I'm going to give it another global scope that it can refer to. And in that global scope, the shadowing doesn't exist. Where I think that that is maybe a little bit flawed is we wouldn't know if there's a symbol that's necessary that would be defined later. And so it's likely that you could have a name error here where, you didn't quite, get the right global scope, or there could be a change in names. For example, any sort of monkey patching that occurs, and then you wouldn't be reflective of that because you would have a shadowed scope. However, what you could do, Akshay, is I have to see if this is possible, if you could make the global scope a chain map, so you only override the symbol with the one that you want to keep, and then you have the other global scope. I don't know if you can do that, though. I think your globals has to be a strict dictionary, but that I have to take it and find out.
I think, you can make a chain map, but like you have to store like the global scope as a chain map, so I don't think we would necessarily be updating the globals variable, the output of the globals variable using a chain map. I don't think we can have that because it would be a mapping, and I'm not sure if it's a mutable mapping or anything like that.
I'm not certain. I think you can use dictionary subtypes for your global scope, because that's how prepare works. You can provide anything.
Type.prepare. Okay, then the prepare. Okay.
But I'm not 100% certain that. I have to think a little bit about whether that'll work in this case. Your local scope, however, historically was not really a dictionary. It was flattened into a C array. That's why it's load fast, not load local. But they're actually going to change that, I think, at some point in the near future, and make it an actual proxy dictionary of some sort.
Also, I have when you mentioned about like using function type and the high order function. So basically, are you trying to make sure like the global reference becomes like a non-local for that particular function?
So what you do is you turn that into basically a load deref for a non-local. It's probably the best thing to do. You don't want to make it a load fast. You want to make it something that's outside of its current scope, but that's not a global scope thing. So I think you turn it into a load deref.
Okay, so basically we're just going once. So we're just making one stack.
One step up.
Like we're just popping it up.
Yeah. I think, and the reason you have to use types, or what is it, typing or types.function type, is you can change a function's code object, but you can't change its closure object. The closure object is still read-only. So you'll have to replace the function entirely with something with a new closure.
Amazing. All right. Well, I love it. Most overkill answer to one of these fairly dumb questions, but I mean, to get under the hood like that, thank you guys. That I'm sure we could talk about this quite a bit, maybe even come up with the next Python release. But I think we should get back to the meeting. But thanks, guys. That was awesome. All right, let's get back into our intro now that we've gotten through our fun little quiz. 25 minutes of learning how Python is working. All right. So if you guys didn't notice, Python logo shows you how you're actually supposed to say. Like coding. Akshay's killing it. He's got it. All right, so it's August 1st in well, Pacific time, Eastern time, not in DN land, not in Auckland. But all the same, welcome everyone. Maybe we should start putting episode numbers on these things. There's over 1,700 of us in the meetup group. 1,756 as of yesterday. Proud of everyone. All hail our glorious founder, Josh Miller. Got us started in February 2017. Robert and I have been running it since January 2020. Everyone's been cool lately, so I don't really feel like I need to go through this. So yeah, thanks for being cool. We're inclusive and just mind your P's and Q's. Meeting format in general is we like to open the floor to questions as we go along, makes it a little bit more dynamic. Also, it tends to only be a few dozen people, so it hasn't been too crazy. But if you're gonna drop in, please don't sound bomb or hot mic. If you're feeling a little shy, please use the raise your hand function or drop a question in chat and we'll try to stay on top of that. Visit us on Slack and Discord, Slack at sac-tech.com and Discord at sacpi.org.com. We're also on X, tweet on there from time to time. Got a bunch of users. Follow us on there. I think we're approaching 300 users or followers right now. And we're on Reddit. I post the videos there. I don't post the meetings anymore because that's when we need to read the code of conduct. We're also on Facebook. Literally dozens of us are on there. That one's been kind of a ghost town. Sorry, Zach. We're on LinkedIn too. Ooh, I should put another link up here. We've got a group. Join the group. We've also got a page, or I guess it's called a showcase. All the same, we posted that on LinkedIn. And thanks. I'm realizing that LinkedIn's actually kind of the way to go because when we get a cool speaker like James, you can tell what James has done. If you got a speaker on Meetup, you get to see other meetups they're in, but other than that, it's not a lot of people put a whole lot of effort into their meetup profile. We've got a YouTube channel that my company hosts, Brazen Studios, and I post all of the good meetup recordings there. So I suspect, based on how things have started tonight, we will be posting this one. Right, we're gonna do a quick community shot. I welcome everyone to turn on their cameras and make sure your lighting's looking decent. If you're dressed as well as James Powell, please, by all means, put your camera on. James is looking sharp. All right, I'm gonna drop the share and put it on gallery mode. Oh, that's right. Updated thing. It's in gallery. All right. Oh, good. Twinkle's made it. Oh, nice. All right. Everyone looked like you understood that last coding challenge. Get a few screenshots. Great. All right. Thanks, everyone. And time to start pivoting towards our feature presentation for the evening. As you can tell, we've got a genius among us by the name of James Powell. He is the founder of a company called Don't Use This Code. They are a consulting firm, an education firm, a coaching firm. He's also chairman of a group called NumFocus, which is a sort of maintenance steering organization for all of some of the most important underpinnings of the current AI movement. NumPy and pandas, which we'll be talking about tonight, and a handful of other really important things. One of our previous speakers, Travis Oliphant, is the founder of that organization, and it was one of our better meetings. So I'm pretty excited to have another NumFocus guy on board to talk. Tonight, James is going to be talking about some simple financial portfolio analysis using the pandas data module. So without further ado, I'm going to pass things off to James. Once again, thanks for joining us. Can't wait to see what you got in store for us.
Okay, I'll get things started by sharing my screen. Behind me, you should see my screen. I'll hide in the corner here. I'll also double share my screen. This is simple portfolio financial analysis in pandas. My name is James Powell. It's Thursday, August 1st, 2024. We're at CalPy. If you like this presentation, well, we have a link here with some additional resources, our mailing list, our newsletter, as well as our Discord channel that we'd encourage you to join. We also have a YouTube channel. The premise of tonight's presentation is, I don't really want to show you that much financial analysis because honestly, I'm not a financial advisor and I don't want to give you advice on what you should trade or what you should hold in your portfolio. Also, largely, a lot of those presentations, honestly, I don't think they're that interesting. Instead, I want to show you how to solve very simple financial analysis problems in pandas. And even those kinds of problems, honestly, for those of you who don't have any experience in this domain, don't worry. It's not going to require any specialized knowledge. We're going to do some very, very, very simplistic accounting level analyses. Our goal then is to better understand how to use pandas the tool, or to understand some details of pandas that I think are often overlooked. Pandas the tool that we could rightfully say is ubiquitous when it comes to analysis of columnar data. And as we'll see, standard pricing and trading data is oftentimes in this particular formulation, it is columnar. It is a tool that is oftentimes the subject of complaints, where I think that those complaints are often driven by a couple of different factors. One factor being that the tool has evolved and has changed quite significantly since it was first introduced. Another factor is that the tool doesn't really give you a strong indication of how it's supposed to be used and the coherence of its own design. So when you read the documentation for pandas, it's often the case that it doesn't really tell you about index alignment, thinking in terms of indices, where this is really the one singular coherent theoretical construct behind the entire tool. And it's very easy to overlook. Also, because people try to bring approaches that they use in R or MATLAB to pandas, where pandas is something of a different entity. A pandas data frame is quite different than an R data frame, even though they may have the same name. And then finally, because even though pandas has a very coherent design, it is a very inconsistently implemented tool. As we'll see, the pandas API is kind of all over the place. It has evolved its coherence. There are still some aspects of pandas that are under active development or need to be completed. It isn't the case that if you see in pandas a method for A, B, and C, then you're guaranteed to see D or E. It's likely to be a case that you have A, B, C, and then you skip down to F and G, and there's all sorts of little bits and pieces that you might have to work around. For all of those reasons, oftentimes people find that they can do really simple analyses in pandas. They can do group bys, they can do columnar aggregations, but then they struggle to do anything more significant because that theoretical underpinning, that understanding of how the tool is designed and how to use the tool appropriately is missing. One very big area of it that we're going to see in this presentation is it's very rarely the case that people seem to write good functions that take pandas data frames as their inputs and return pandas data frames as their outputs. It's often the case that this stuff is very brittle, very ad hoc, and there's a good reason for that. There are many details that we're going to have to skim over in this presentation simply because we don't have time to go into them about how pandas is designed, how pandas works, and some other theoretical details such as the ideas of restricted computation domains, the ideas of homogeneity, looseness and strictness of homogeneity, or the ambiguity of homogeneity. There's quite a few of those. We'll try and touch upon those where it helps us inform the presentation a little bit better, but we're going to pay attention to time and we're going to try to get as much detail as we can in the time that we have allotted. Here's how we're going to get started. Well, we're going to get started by looking at just some basic pricing data. And for most of these examples, it's sufficient for us to just work with simulated data. So what I'm going to do is I'm going to, in pandas, simulate 10 years of pricing data that's captured between the hours of 9:30 and 4 p.m. when the market's open. I'm going to assume that I have price every 15 minutes. And that's going to give me something that's going to be relatively large, a couple million rows, although not too large that the virtual machine where I'm running this code can't work. I'm going to assume that I'm trading in a very simple space, some kind of equity space. So I'm going to randomly generate 54-letter stock ticker names. And we're going to assume that for each one of those stock ticker names, well, for each one of those names and each one of those dates, we have some kind of price. To make the example just a little bit more interesting, we're not going to assume that there's one single unified price. We're going to assume that there's a buy price and a sell price. And maybe there's even some slippage when you try to purchase something at a price maybe you hit that price, or maybe you get somewhere around that price. Maybe you strike a better deal or you strike a worse deal. The buy price is merely what you can buy something for, and the sell price is what you can sell something for. Anybody who's played a video game, you know that one of the worst ways to make money in a video game is to go to the merchant and to sell all your best equipment and then to have to buy it back. Because the price at which you buy something and the price at which you sell something, there's always a margin there. You always lose money. And so you need a little bit more smarts. Now, we're going to simulate this data as a simple random walk. And so what we discover is that this underlying pricing data set doesn't really have any interesting patterns. It's really just enough data for us to demonstrate the code for how we would do this analysis. So here we have our data frame that's indexed on a multi-index with the dates and tickers. We have our random walk for our buy prices. We're computing our sell prices as a strict margin below the buy prices. It is the case in the real world that sometimes you see some inversion of that spread where something can be sold for more than it can be bought for, but that's quite rare. And in this case, we'll just eliminate that, even though the detail doesn't really matter for what we're going to look at. And we'll save this to a pickle file so we don't have to rewrite that code. So you can kind of see this is what the data looks like. You know, for every unit of time, we have these assets. ANRQ is one of our simulated ticker names, and we could buy it at $165, or we could sell it at $161. So if I bought 1 million units of this and then sold them on the same, immediately after, well, I'd lose money. So probably what I'd want to do to make money here is I'd want to buy it and then hold it until some time later when the price goes up. Here you can see an index slice. Well, it looks like for this ARNQ name, for this 30-minute window of time, I basically better keep holding this thing because no matter what I do, if I try and sell it, I'm going to lose money. Now, from that, I want to generate some trading data. And I want to show you the naive approach that people use when they generate or they think about this kind of trading data. And then we're going to do some analyses. And we're going to discover that the analyses in some cases are actually quite difficult to do correctly as a consequence of the improper formulation of this, that is using a data frame where in fact a series is probably a better structured object. To create our trades, what we're going to do is we're going to take all the dates that we had. We're going to generate a multi-index from those with all the dates that we had, all the tickers we had, and just a counter from 0 to 10. We're basically going to give ourselves, for every pricing mark, for every unit of time we have there, 10 chances to purchase or sell that particular asset. Then we're going to sample that down to 5% of the data. So if we had a couple million rows of this pricing data, maybe we'll have 1 million trades that have been randomly selected there, where sometimes we could do true trades within the same unit of time. To make this a little bit more realistic looking, we're going to take those dates and we're going to noise them up. So you don't trade exactly at the 15-minute mark. You trade a couple of minutes on either. I think here, this is a couple of minutes beyond that mark, just to make it look like real data where you have trades that come in between these. And we're going to compute the volume of that trade, where that trade has a positive volume if you purchase something or a negative volume if you sold something. You're going to trade in units of about 100 to 100,000, but in lots of even nearest hundredth size. We're going to use our pricing data to figure out what the price you would have traded that at is. And to simulate a little bit of slippage, we're going to smudge those prices. So if you had to buy it, we're going to smudge that by just a simple normal distribution here. But note that that is a two-sided distribution. So sometimes you could do better than the buy price. Sometimes you do worse than the buy price. Just to simulate that, in the real world, sometimes the price is something, but some people can make a better deal, or some people make a worse deal. And the same thing with the selling. And we're going to, just for the purposes of keeping all this data aligned properly, we're just going to remove anything that falls outside of our pricing window. So because we shifted those dates, maybe we accidentally pushed one of these trades a little bit too far into the future. We don't have any information for what the price should be. We're just going to eliminate that. So if we look at our trades take just a moment to generate. We're also going to save this. We have about 2 million trades here, and our trades look like this. We apparently purchased 40,000 units of HVRA, and we paid $200 for this. Hopefully we got a good deal here, or if we didn't get a great deal, hopefully we sold it later for much more than it was worth. We did this, and you can see here where the smearing or the adjusting of the dates, we did this 44 seconds after 9:30, just to represent that we trade on continuous time. There are a couple of details hidden within that analysis, but it should be enough for us to actually get started and look at how we do some basic portfolio analyses. Now, the portfolio analyses that we'll look at, and I don't believe we'll be able to get through all of them, are just a couple that run us through some of the basic mechanics of pandas, where we're going to have an opportunity to see where traditional approaches, where this naive formulation with the data frame actually works worse than a slightly more sophisticated and slightly simpler. And so we'll start off with something very simple, which is average price. And I think average price is interesting to look at because a very interesting analysis we can do later, if we have time, that takes a bit of sophistication, is average trade price. But average price just means, what was the average price of one of these names over that 10-year window? So if we had our prices, and our prices look like this, well, the average price is just grouping by the asset and then computing an average. So in pandas, this would just be group by asset mean. Now note that this structure has two columns, a buy and a sell, but the mean is just going to give us the mean of both of those columns. And so here we can see our average price for all of these. Now, one small detail that we'll use later is that we've made these categorical. We're going to only do the mean of the triggers that we observe in the pricing data, just in case there's something missing, and that'll eliminate those two NaN columns. So very simple analysis. You can see ARNQ on average over that 10-year window traded for $460 or sold for 57 bucks. This is pretty much how far most pandas information tutorials, books, or whatever go about to this level of analysis. But there's much more that we can do with this data. For example, we could ask ourselves, well, how much cash changed hands? How much did we actually get in what you might call realized P&L? When you think about your portfolio and you think about the profit or the loss that you've made, you can distinguish the realized profit or loss versus the unrealized profit or loss. And that's a very important thing because, as you know, you don't lose money until you liquidate the portfolio. Just because the stock market is doing badly doesn't mean you haven't lost anything. It's only the case when you sell all your stocks that you then realize that loss. Well, here the total cash here is just the realized P&L, how much cash actually changed hands, so how much money you have locked into your bank account, and it's a very interesting and very useful analysis. For our information, that's just a column of our trades data, so all we'd have to do is take the volume, multiply times the price, and sum that up. So we could say take our, and I'll do this with a pipe just to make this a little bit easier for me to write. We could take our volume and we could multiply it times our price. That gives us the cash that changed hands, but the sign on this is incorrect because we said that if you purchase something, the volume is positive. Well, if I buy something, I have to give you money, so this should have a negative sign here. Then what I can do is I can just sum up this value, and you can see this is the total amount of money that changed hands. One downside of this kind of simulated data is that it doesn't really show you any patterns, and sometimes the numbers look a little bit wacky. It looks like we have done very, very badly. I don't know how many digits that would be thousands, millions, billions. We have lost $166 trillion in our simple portfolio or simple trading simulator here. So obviously this is the limitations of dummy data. Sometimes we get dodgy numbers, but the code itself is the exact same if this were real data or not real data. Now, an interesting thing that we might ask is, what is our life-to-date position? How much do we hold of each one of these holdings? How much do we have in ARNQ? This is something which you probably would get in the mail every month. This is how much you hold in your stock portfolio. And if we think about it, we have our trades. Well, that's just a group by the trades. We grab our volume column and we sum this. And this gives us what we hold. We probably want to only look at the ones that were actually present because we probably didn't trade in every single name, or maybe we did. And so you can see, as a consequence of the trading data being, or the trades themselves being generated randomly with no notion of the sentiment of how you feel about these things, or no asymmetry around whether you buy or sell, it looks like we have a lot of short positions, negative positions, as well as a lot of long positions. And it looks like we're kind of all over the place, but you'd expect something like that out of simulated data. I will point out one very interesting aspect of this to all of you. I have been doing examples like this for years and years and years. In fact, tomorrow I'm doing on the O'Reilly platform a 5-hour presentation on all the details of how to use pandas well. When I do these, I use 4-letter randomly generated stock names, and I have yet to get in trouble. Look, all of those stock names, not a single bad word. And so I must have some pretty good luck with my random seeds. One day I'm going to get in trouble, but today is not that day. Now, setting that aside, another interesting aspect we might have is, well, what is everything that we hold worth? And this is where this data set starts to get a little bit dicey. Well, what does it mean, what is everything worth? I guess that would be something like, what is our total holding worth? So that's not too hard. We could get our life-to-date position and then figure out what each one of those entities are worth as of the current date. But one thing about this market value is, well, we're starting to perform aggregations of the data. And oftentimes when we do pandas analyses, one of the things we want to try to avoid is aggregating any data too early in the process, because as we know, there's some entropic loss of information when we perform an aggregation. And tying that back to the original data may become problematic if we eliminate the information of, this is one trade and this is one trade. For example, somebody might want to ask, what is our market value per trade? How much did the trade that we do on Tuesday contribute to the total position that we have on Friday? And how much of the market value on Tuesday contributes to the market value what we have on Friday? And you could think that this could be, for all these attribution questions are often trying to trace back and see why is it that we lost $166 trillion? Maybe that was one really bad trade. Maybe that was a sequence of bad trades. Well, it's random data. It's probably a consequence of that more than anything, but you get the idea. Well, what we could do is we could say, okay, here we go. We have our holdings, and given those holdings, this is a structure that's indexed on the asset. And what I want to do is I want to take my prices, and I guess I want to take my prices for the very last day that I have. So we'll look at our prices here. We'll do a head 3. Okay, so that's indexed on the date and the asset. We'll look up something based off of that index. So we'll look up the last signal that we have for the date. So we'll do prices.index.getLevelValues, date. We'll look up the maximum here. And so now we have all the prices as of the very last minute that we have on the buy side and the sell side. Okay, now this part's a little bit tricky. If we just had long trades, what we could do is we could just get the buy column, and you could see this is indexed on our asset, and this is what we would buy everything for. And we could take our position, and we just multiply these. And here, this would be what our market value is per position. This is a very classical use of index alignment in pandas. Whenever you do an operation on 2 pandas structures, it looks at that index and figures out how to match up corresponding pieces of data. So it looked at the trades and said, in ARNQ, I have such and such volume. Looked at the prices. For ARNQ, I have such and such final price. Match those up and perform the multiplication. I could even use something like the mapmul operation here to do a aligned multiplication and then a sum here. You can think of that kind of like a dot product operation. You can see that even though I spent a lot of cash, I have a lot of market value. And if I'm lucky, what my holdings are worth is greater than the cash that I spent to get those holdings. I don't think that's the case here. It looks like I have $23 trillion of market value, and I spent $166 trillion to enter these positions. So the good news is, if I liquidated the portfolio, I'm only losing $140 trillion. Still a little bit better than $166 trillion, but maybe not by that much. The problem here is that assumes that all of my positions are long positions when they're not. My positions are sometimes long and sometimes short. And so I need to figure out how to do this aligned operation between these. So let's take a look at this. Let's look at our sum again. So what I need to do is I need to figure out, okay, for the ARNQ, I want the sell price. For the CWAO, I want the buy price, and I need to match those up. Now, there's a couple of different ways that I can do this, and this is one unfortunate thing about pandas, the way to do this in the most fluent, most adhering to using pandas tools and pandas mechanisms, it actually ends up being a little bit slow as a consequence of the inherent slowness of index alignment. So here, just to work around that, I'm going to use instead a little bit of NumPy. If you are looking to improve your use of pandas, and you're looking to improve it a margin over your colleagues who are also pandas users, I would argue that one thing that is very underlooked or very underappreciated, but is critical in any actual real-world pandas code is, does this pandas code interact and interoperate nicely with the pure Python code that's setting up the data pipeline or that's setting up the report? And does it interact nicely with other analytical tools like NumPy? And it's often the case that people who know pandas very well don't quite know how to dip into NumPy and how to use NumPy in concert with pandas. And it's very often the case that pandas users often really struggle to figure out, well, how do I use all the rest of Python nicely? I have some really good analytical code, but the analytical code's not worth anything unless it's embedded in a data pipeline, a reporting structure, some sort of application for an end user, unless it's actually embedded within the business process. Well, here, what I'm going to do is I'm going to do it with sign, or I could do it with just where. Let me show you both ways. NumPy sign gives me the ability to find the sign of a value, as in the positive or negative sign. So I could take these sums, and I could figure out the sign of these values, and you could see a +1 or a -1. I could create a series object that is indexed on these signs with a +1 and a -1 like that. And I could do a .lock operation with these to get, and here we'll need series from pandas, to get whether it was a buy or sell. I could then take my prices structure and I could unstack this buy or sell column like that. And I could use this buy or sell information to index into this structure. Well, that's not too hard to do. That would be a .lock. And anytime I want to do a non-Cartesian product .lock here, what I'll do is I'll create a multi-index from arrays. And I'll use as the first array this thing that I just created. And as the second array, and I actually need to use this twice. So that's going to be a little bit ugly here. Since we're doing it all in line, we'll just copy it. But you can imagine that we could store that to a temporary or some such. Index get level values asset. And this will then perform my lookup. Now let's make sure that we have everything closed here. And you can see here, it's now pulled out for each one of those, the actual appropriate price, and then I can multiply it times this structure. Well, to actually do this a little bit nicer inline, the way we'd probably do this is with a pipe. That way we can refer to this thing 3 times. But this is quite clumsy, and we will notice that if we do this on large enough data, it's actually quite slow. This index alignment is not a fast one. And so the alternate approach that we might use, let's get that going, and then we multiply this times the df. That should be good. Oh, and here we need to remove this from before. There we go. So here you can see this is our market value there, and then probably we drop that direction level because it's no longer that interesting. So that's one way to do it, but unfortunately, visually very clumsy and quite hard to follow, and also, trust me, in practice, it's actually kind of slow. So instead, what we'll do is we'll take our prices. Actually, we'll take this same value. We'll take our prices, and we'll just do a single .lock. We'll do a single .lock here on just the asset, and that'll give us the buy and the sell price portion, and then we'll use a numpy.where. And normally this is, just one of these cases where the numpy approach is going to be so much faster than the pure pandas approach, just as a consequence of sometimes that index alignment. There's performance degradations, there's gaps where they haven't added fast paths, and as a practical matter, we just have to use pandas as a very practical tool. We can't hew too closely to what we think is the ideal way to do this. So here we'd say where, and we want this on this original thing. So here we'll call this PX. We'll take this original thing. This should be where this is positive. We'll use for liquidating a positive, we're going to use the sell price. And if we're liquidating a negative, we'll use the buy price. And so in the previous one, we actually had swapped that. One small detail here, we actually want to swap this because we have to move in the opposite direction of the directionality of the trade. Buy if we have something, or sell if we have a positive volume, and buy if we have a negative volume. Taking that, we can multiply that straight times our DF, and we get the same result, just with a little bit less mechanism, a little bit less visual noise, and trust me, this is going to be considerably faster. Probably the most interesting thing that we can do is to look at our P&L, and this is where we're going to start seeing a very common approach that people take in pandas that in this particular case will appear to work, but it's going to start getting really messy. A lot of pandas code has this particular style of take a data frame and just add more columns and keep adding columns until you've added all the columns for all the things that you wanted. So it would be very common to see somebody take our trade structure and say, let's add a column with the cash that changed hands. And that would be the volume of each of the trades times the price that we traded at, that traded price with a negative sign. We've done this one already. And so now we have a structure that has, and here we'll just do a .head3 so you can kind of see this. So there we have the cash that changed hands. Okay, now that we know the cash that changed hands, let's figure out the price at which all of these were traded. So that's kind of this example here. Here, this is the market price. So that's what everything is worth as of our last day. And here again, we may have to change a couple of variable names, but this would be DF, that's good. And then we're going to take, and here we're actually going to not do the group by, we're going to use the original volumes. So we'll take our original structure and we're going to just think about this. We'll take our prices, we'll get the assets that we have. If those are positive, we'll sell them or buy them. So we'll get this on an aggregate basis. So I think we just have to do that. And we have a broadcasting error. Let's see why that is. And it's because here we've indexed this down to the final date. Oh, and we need to, let's see what we have. This is where this approach starts getting quite clumsy. So one of the tricks we'll do is we'll pull this out. And here we'll do trades. Okay, so that should be of the same shape as our trading data, 2 million rows with the buy and the sell. If we do this, that should give us that. And we'll see why doesn't it want to broadcast these. It doesn't want to broadcast these because, oh, because it should be trades volume. That's why, because we had a series before. Okay, very good. And so this would be what our market price is. A very common way you see pandas use this, just stack columns until you've got enough columns to answer any question you want. And to a large degree, it seems like it works. You know, you can see we just keep going and the market value for each of these would just be now the volume times the market price. And then finally, you can think that our P&L, our profit and loss, well, that's just going to be whatever cash changed hands plus whatever the current value is if we liquidated. And here we go. And now we have the profit that we made on a per trade basis. This is the typical way that it might be done. Notice we're not projecting this down yet. So at the very last step, then we could do something like group this by the asset, grab the P&L column, and compute the sum. And so this is how much profit we made on each name. This might be useful for us to identify if the reason that we lost money was a consequence of 1 or 2 bad trades or a bunch of bad trades. It looks like we are basically terrible at trading. We always pick the losers. We always buy high and sell low, except in 1 or 2 cases where we made some money. So this is why we lost so much money here. But this illustrates our typical pandas approach. Now, given this approach, one very complex question that we're going to have a lot of difficulty solving within this structure is the average trade price. I think the average trade price is actually one of the most interesting questions, especially if we think about what this means. It's commonly the case that what you want to do when you're looking at this information is say that the market prices aren't real. And I kind of agree with this sentiment. You know, a price that you see on a ticker tape on television only represents what people assume somebody out there might buy or sell something for. But that's not a real price that exists. The only thing that's real is the actual money that changed hands if you try and execute a trade. Just because I say I'm willing to buy something for $10 doesn't mean that I'm actually willing to buy something for $10 until we transact and I give you $10 for that thing. As a consequence, what you can think is that while we have those prices that represent the market, the real information, the real signal that we have is the trades that occurred. And so what we might want to do is we might want to ask a question of what was the average price, not given the pricing information that we saw, but given the actual trades that we performed. What were the actual trades at which, the prices at which we saw somebody was willing to buy or sell this thing? And it's commonly the case that we want to try and batch that up based off of our strategy or our notion of why we went into that trade. So what we want to do is we want to identify what our positions were. How often did we have a long or a short position, or did we trade in and out of that? And this requires a little bit of sophistication, the reason for which is if we want to identify for one of these given names what positions we had, not what life-to-date aggregate positions we had, but what cumulative positions we have, what that means is we're taking our trading data that looks like this, and let's index slice this down to just one name so we can see what the idea of this is. So HVRA is a good name. So there we go. And what you can see is here, these trades all constitute the same position. We thought HVRA was a great thing to buy, so we bought some more, we bought some more, we bought some more, we bought some more. At some point in the future, we might have closed out that trade. We might have said, no, HVRA is no longer worth holding. We could have closed out that position. And that's when we would consider it to be a brand new position. What we might want is we might want the price over that span of time when we were really bullish on HVRA, and then the span of time in which we're very bearish on it, and the span of time that we're bullish on it. And the way that we do this takes a little bit of sophistication because we can't just group by the asset and answer this question. Because unlike the Python itertools.groupby, the pandas group by pre-sorts the data. So it's not going to give us the sequences when we had a long, and then the sequence we had a short, then a long. It's just going to give us all the longs together and all the shorts together, or all the buys and all the sells together, I should say. So what we have to do is the following. We're going to take this data, and we're going to try and identify what are the sequences for which the cumulative position that we have was in a set direction. So we'll start by doing a group by transform on this data. We'll look at the volume and we'll do a cumulative sum. And this will tell us what the cumulative sum is over time. Now, of course, in modern versions of pandas, we have to do an observed equals true, otherwise we get that nasty error message. And so you can see as we start trading up, the volume will keep going up. If we bring our index slice back in, you'll see instead of having the incremental trades, you can see, okay, yeah, we're just keeping stacking onto this thing. And if we're following the traditional approach, this would just be one more column. We'd have cash, market price, market value. In fact, I'm even going to do that for you just to show you how people do this. Because this is where it starts getting extraordinarily messy and where cracks begin to appear in the approach that basically everybody uses for doing these kind of analyses. And honestly, it's the approach that we used to use until we thought about this problem very deeply. So this would be your cumulative volume. And here that would be df like that. And this is going to blow up on us with a spurious index alignment. So here, there we go. And I think this, yeah, that should be fine. So you can see for the HVRA, we started off with this and our cumulative volume is, and it'll just kind of stack up. What we can do there is we can get the position direction. You can see what I mean by just stacking columns. It's just column after column after column. Our cumulative volume, like that. And that gets the direction of the position. And then given the direction of the position, we can actually number these positions. So what we'll do is, this is where we need a little bit of finesse. We can't do a group by the position direction because it'll just take all the longs and all the shorts and give us 2 groups. We have to look at how that changes over time. So what we'll do is we'll take our position direction. Let's pipe it so we just get a series here, make it a little bit easier for us to play around. And what we're going to do is we're going to, and I'm going to just print out the position direction and the position number, just so you can see those. Otherwise, it makes it a little bit hard for us to see everything. Okay, what we're going to do is we're going to compare this against itself shifted. So we can see, are we the same as the previous value? So you can see when we actually have to do this in a group by. Otherwise, we're looking at cross assets, which is not correct. So here we have to do a group by asset, and then inside this, we have to do a transform. Given the group, we have to look to see if that group is not equal to itself shifted. And this is then going to say, okay, these HVRAs were long, and then it switched into a short position. And from this, what we're going to do is we are going to compute a cumulative sum. Now, we'll have to do an observed equals true. And here you go. This is how you can identify where something changes in pandas. So you can see by the end of this, we had 294 unique positions on UWCB. With that, we're going to take this position number. We're going to stick it into our index. This is what? Set index position number. Append equals true. We'll do a sort index. And then we'll do a group by asset and the position number. And here, if we wanted to buy or sell price, we could actually get the position direction as well. So we could do the buys and the sells. And this just starts getting so clumsy that we may ask ourselves what's breaking here. But I think its price is just the traded price and the mean. And here, okay, once observed equals true, and let's do an observed equals true. And some of those nans are fine. That just means that we didn't actually trade in that name. And what I'll do is I'll unstack the position direction, even though, as you'll see, those values should have been long and short, shouldn't have been 0, -1. So you can see kind of here, these are netted trades. But for ZYRZ, this was strictly a short position, and it traded at an average price of $40. And you can see all these nans here. Something has gone wrong along the way. So what I want to do is I want to shift to a very different approach to model this data. Even though it is extraordinarily common for people to use these data frame tools by just stacking columns and columns and columns. Every question we ask, just one more column. Every question is just in terms of the previous column. So these things get wider and wider and wider. It turns out that it just becomes clumsier and clumsier for us to represent this data, especially because there's a couple of aspects of this data I really don't like. One aspect that I really don't like about this data, setting aside any of the actual computations we did, is that some of these columns represent individual entities. This represents the trade that this one entity had. And some of these represent cumulative, which means that if I resort this data, some of these columns are no longer correct and other columns are still correct. does this data frame contain individual row level information, or does it contain aggregate information? And the inclusion of cumulative columns seems to break that almost immediately. And you could think that basically for this position analysis, for the average trade price analysis, everything to the, from that cumulative volume to the right is now an aggregated column. And it starts breaking our conceptual model almost immediately. It makes it difficult for us to compute these analyses, and it makes it difficult for us to really think, what does this data frame contain? And so what we're going to do is we're going to model it very differently.
James, before we move on, Deanne had a question. What is
Okay.
the cost of adding columns to a large data frame? Are they added, or is a new data frame created?
One of the things that makes it very difficult for us to assess the performance of pandas is that pandas is much more opaque than a tool like NumPy. And if you take a look at a pandas data frame, you will see that the data in a pandas data frame is stored in what's called the block manager. So if we look at a pandas data frame here, you can see here is, it doesn't want us to look at this, but here's our block manager. The block manager is what manages the data behind the pandas data frame. Typically, adding a column to a pandas data frame is effectively a free operation as long as we're not counting the index alignment. So for example, if I have a data frame here that has a column A, 1, 2, 3, like this, and I want to add in another column B, 4, 5, 6, this here is not going to copy the original data in that data frame. Likely, the block manager is just going to give us two blocks. It's probably not going to merge them. You can see that's exactly what happened here. We had 2 blocks. It didn't merge them, so there was no copy. So this original data was just wherever it was. This data was wherever it was. Now, obviously, it's going to go from the Python data to this pandas data, but if we really think about what this would look like, we'd probably start with something like that. You can see these are separate, which means this assignment all by itself, no copies, basically free. We're just throwing a little bit more data into this container. However, there is necessarily the cost of the index alignment. Let's say that this is an index structure. Let's do a to-date time to make this moderately interesting. So here, let's give it, I guess we have to have 3 dates. There we go. And then here, we're going to make this a series object. Even if it's a series object, it's likely it's just going to grab the data out of it. But if we give this a little bit of a non-exact index comparison, like something like that, well, here it's actually going to have to do a little bit of work to figure out how to align these. Because if we look at the data frame, we'll see it's going to have to, and it may have to do a copy in order to do any NaN filling here. You can see, actually, it wouldn't have to do a copy of the original data, but it has to do a copy of the data we passed in to, throw away the non-aligned piece and to do an NaN there. So if we're just doing an assignment like the ones that I've done here, because these assignments are assignments using the original data frame and then performing subsequent computations, it's likely that the entirety of this computation is giving you an exactly same index to the original. Pandas will see that the consequent of the highlighted code has exactly the same index as the original structure. It'll skip the index alignment. It says I don't need to do anything there. And the only thing we're paying for is this computation. The actual assignment of the column is otherwise basically free. Except the block manager is allowed to combine things as it sees fit. It's allowed to split things as it sees fit. Block manager may decide to do a copy because it wants to bring 2 pieces together, but it doesn't necessarily have to do that, and likely it probably wouldn't. And so it's dollars to donuts, probably just the cost of the computation and no additional overhead cost. I hope that answers your question. Now, with that said, I want to show you a different approach. And one important detail of this different approach is to use pandas the way that it was intended to be used, to acknowledge gaps in the pandas API, but to also acknowledge that, this is something that I think we oftentimes forget. Many of the tools, if not almost all of the tools that we use, are tools that are on active development. I don't know how many times I have looked at a colleague's SQL code and I was like, oh, you learned SQL in 1997 and then never read a single thing about SQL ever since. Or shell scripting code or matplotlib code, it's all the same. And you're like, these tools are under active development. They come up with new standards every other year. There's new features. Maybe we should keep up to date with all of those. It is very much the case that tools like NumPy or tools like matplotlib don't move that quickly. And so if you didn't really keep up to date with changes in NumPy, yeah, maybe a couple of years will pass and nothing too major will have changed. But Pandas is a very actively developed tool, and it's very likely that between versions, from Pandas 2 that I'm using here to Pandas 3, you may see hotspots. You might see places where optimizations weren't added, where fastpaths are missing, where features are missing, where methods are missing. Those get filled in. Well, to acknowledge that, what I'm going to do is use Pandas API extensions to register an index accessor. Because the approach that I want to take here relies on a couple of operations where I'm going to change the indices. I'm going to work with just series objects. And I'm going to implement two missing methods. We can drop a level of a multi-index. We can swap the levels of a multi-index. But for whatever reason, nobody gave us the ability to add a level or to update a level. It just hasn't been done yet. And it's a lot of clumsy code to do inline. So what I'm going to do is I'm going to create a namespace where I'm going to add in these missing pieces of functionality, and then I'm going to use them. Well, the nice thing here is, the way I use it is, I take my index object, I go into my little namespace here, and then I use my method. And I've modeled the implementation of this method to be as close as possible to the ones that do exist, drop levels, swap levels, so forth and so on. So maybe, hopefully I'm within spitting distance of how this might look if somebody actually did add this to Pandas. And if that happens, and the day that happens, well, I can put a warnings.warn to warn somebody, don't use the ._x, that's deprecated, use the actual official way. Hopefully it's as simple as just doing something like that. And nicely, it's a very easy to grep for thing. I'll grep through my code every so often for my _x to see all the places where I worked around gaps in Pandas. And maybe I no longer need to do that because a new feature has been added. And you can think that here, that _x should be just visible enough that it can, that's never going to be broken up, but you can imagine that this could get multi-line. So doing _x.add level might be a little bit harder to grep for, but just that _x should be short enough and should be contiguous in my code no matter what. So it should be something I can just quickly scan through, okay, where are all the places I've tried to extend Pandas. Well, I'll write that out and get that ready to go. I'm going to reconstruct my trades. And what I'm going to think about is, it's often the case that when people talk about the dimensionality of their data, they talk about Pandas, they believe a statement in the Pandas documentation that says that a Pandas data frame is two-dimensional. I'm here to tell you Pandas data frames are not two-dimensional. They are collections of one-dimensional data. If your data is two-dimensional, don't use Pandas. Use Xarray, use NumPy, use another tool. Pandas is what happens when you go out into the world and you collect a one-dimensional data set, like the price of something over time, a time series data set. You take that data set and you label it in some fashion. Oh, this is for the first of the month, this is for the second of the month, this is for the third of the month. That labeling could be hierarchical. This is for ABC on the first of the month, this is for ABC on the second of the month, this is for XYZ on the first of the month, this is for XYZ on the second of the month. A hierarchical label doesn't mean a two-dimensional structure. It's a big mistake that I even argued with people on Twitter or LinkedIn the other day about. A data frame is what happens when you take multiple one-dimensional data sets that have some alignment and you bring them together into one structure. Data frame obviously has to be homogeneous within a column, but doesn't have to be homogeneous across columns. It's not one data set, it's actually multiple data sets that are brought together. This is one thing why when people try and write functions on top of Pandas data frames, it often falls apart because you can never guess what are the column names there. Do you have to name your columns in a specific way? Do I pick out that exact column? All of those details just make it very irritating to work with pretty much any library code that you see people write. Whereas with a series object, Well, you just get one data set. The series object may have a name, but it's not really used for anything except when you bring that into a data frame. And you can write functions on series objects that are relatively generic, relatively reusable, where the only assumption that you have is not the name of the columns or whether the columns are indexed in, or sorry, the columns are arranged in this fashion or that fashion, but the D type of the data type of the data, and the indexing of the data, how that data is indexed, and maybe some small details, because for example, sometimes you need to know for it's a datetime index what the fidelity of that datetime index is. But usually, like for this example, that's actually not a very interesting thing. So what I'm going to do is I'm going to create my series of trades, and I'm just going to get the volume of those trades. I'm going to use my extension mechanisms to do things like fuzzing up that time. So here, I'll actually build this off of a multi-index that just has the dates, the tickers, and my 10 chances, sampled down to 5%. And I'll construct this entity. Then I'll use my update level to update that date level of my index with my fuzzed structures. I'll sort this, I'll select down to things that are within the range of the data I have, and I'll add one more very important column here. I'm going to put a unique identifier on every trade I have. So every time I have a trade, I'm just going to give it a unique identifier, just a number that counts up from 0 up to 2,711,703. And this is going to be the basic structure that I use. From this, I can redo all of those portfolio analyses, but I end up with structures that are much easier to manipulate without some of the confusions and without this just keeping on stacking on columns approach. I can actually solve almost all of my portfolio problems by just writing two very simple and basic functions. The first is the idea that a trade can be executed. And when we execute a trade, we take the volumes, the things we bought or sold, and the market prices, and we figure out, okay, what date was this thing bought or sold on? What was bought or sold? Okay, give me all the traded prices. You can see this code appeared previously. We can use our numpy.where to figure out, do we have a buy or do we have a sell? We can even add in a little bit of that notion of slippage that we had before. You can see we multiply the traded prices times the negative volumes, and critically, we can update that asset column. Instead of this being, here's a column with the volume and here's a column with the price, we're going to say there's only series objects and they just have volumes. They're either the volumes of the things we traded, the tickers, or the volume of the cash that we received in exchange. So we'll update the asset level of that index to just be the currency that we received, which means with this execute, we'll talk about execute first, we can answer questions like average price is identical, but the total cash, well, we can answer that by just executing our trades and looking at the cash side of the trades that we had. And if we take a look at this, you'll see, for every one of our trades, we just have a corresponding equal and opposite reaction. We just have a certain amount of money that changed hands. If we concatenate our trades and our cash, and then we sort this on our index. Let's get concat, which probably isn't imported. We'll be able to see the two sides of the trades. In the previous formulation, one thing that we would really struggle with, that is a real dimension of actual trading data is, well, you can't always trade directly in a particular currency. We were working with a hedge fund just a short time ago, and as a consequence of regulations in their jurisdiction, there were a lot of things they wanted to trade in other localities where they had to trade out of their currency into the local currency in order to perform or execute that trade, a multi-leg trade as it were. And so here we can even represent something like, in order to buy HVRA, we have to first buy Japanese yen. So we first have to take some amount of US dollars, buy Japanese yen, use those Japanese yen to buy HVRA. And if we want to back out that trade, or if we want to liquidate that trade, do that in the opposite direction. Very difficult to model with the two-column approach, but almost trivial to model. It's just one more row in this structure. Well, here you can see that's just all the volumes that changed hands. That's not particularly interesting to sum by itself because the units are different. But if we wanted the total cash, it would just be our cash thing here. And if we wanted the cash that changed hands based off of which asset was traded, well, you notice we have that trade piece. What we can do is we can join this against our trades. Actually, we can, oh, no, we won't even do it that way. We'll do it this way. We can do a group by. What we can do is we can take our trades. We can pull out the trades corresponding to those identifiers. So what we're going to do is we're going to look at our cash values, index get level values with the, what do we call it? We call it trade. So there we go. So those are the actual trade numbers. We can pull those out of our, okay, and then what we'll do is we'll do a trades.index.get level values. We'll get the trade number here. And this may be another convenience that we want to add in at some point later. And then here we want to probably do a get lock operation to get the locator for this, or to get an indexer. Yeah. Pass that in here, and that should give us the locations of that. And then here, now that wants to do just a single one. So here, what we'll do is we'll take this. This is going to be a little bit ugly, but what we'll do, and this is where a couple of convenience methods is helpful. I'm going to reset index to pull out my asset. I'm going to get just the asset column. I'm going to get just the trade number. So I'll drop my date level. So I have something that looks like this. Now that's a trade number and the asset. And then I'm going to do a dot lock on this using what this looked like. So here I have now how that matches up with my cash. And then what I can do is I can do a group by on my cash. And again, this is where, and we'll do it observed equals true. And that shouldn't be necessary because we're doing this against an exact mask. We'll do this against the dot values. And then here we can sum that. And now we have our cash per traded asset. So again, we can compute this. Well, for our life to date positions, that's not going to be any different than what we saw before. Our life to date positions is really just trade group by asset sum. Here we have all the traded volumes in one structure. Our market value. Well, to compute our market value, what we can think is all the market value is what would happen if we liquidated our portfolio. If we sold everything, that's what that thing is worth. So we can have one more helper function called liquidate. And what liquidate does is it takes our volumes, it takes our market prices, and it just takes some date when you're liquidating something as of. It's going to swap the direction of the trade. I've got 100 units. In order to liquidate that, I need to have a sell, so I need negative 100 units. It's going to update the dates on those, and it's just going to execute that. And so you can see this here is just defined in terms of the execution. So here, let's do the following. Here's my liquidation. I'll liquidate my trades and my prices. And I'll do this as of the maximum date that's available. That's, I think, the default that uses. So my market values, and here, maybe one bug in this. Volumes. Because this example uses, because this example uses this, I have to get these dates have to be, I think those are originally date time, so I think I have to do a start time here. Because we use periods here as well as date ranges, so I think that's going. Okay, and then let's take a look at our liquidation for our market value. This is just our liquidation and just the cash. Is it cash or cash flows that we called it? Cash flows. Just the cash that would have changed hands for our liquidation. The trades corresponding to that liquidation are just the backing out of all the existing trades. So that should give us that piece. Now here you can see that's the market value. And our P&L, really, it's just what happens when we take all of our trades. We take the trades for the liquidation. Well, that's just the reverse of all those. So everything nets out. We bought something for $10 and then we just sold it all out. So we don't even really need to include that. It's really just our cash here and our cash flows here, but we can include the trade and the liquidation trades. We know they'll net out. We got that. And from this, we just group by asset and then sum. And if we had multiple currencies, we'd see, let's do an observed equals true. If we had multiple currencies, we'd see all of our multiple currencies here as well. But here, this will give us, we gotta spell everything correctly. This will just give us 0 for all of the tickers that we had, and then non-zero value for any currencies that we happen to trade in. I think this example only has USD. So if we did that right, then we should see that US dollars, and let's figure out why we have, because we said the cash flows twice, that's why. So if we do the trades there, we should see 0 there, and then we'll select that out. So our P&L is really just the combination of all of these cash flows. Finally, for the positions, you can see just all we had left was dollar bills. And here, the data is slightly different. So here in this example, I think we're losing 34 or $340 trillion. So it's still data was generated a little bit differently, but really didn't add to our luck. For positions and average trade price, where we need things like cumulative volumes, well, we no longer have this awkwardness of having cumulative structures next to non-cumulative structures. Really, the cumulative volume is just take your trades, group by the assets, and do a cumulative sum on this. And if we wanted to figure out what the position number for each of these are, or what position number these contributed to, we can then create an index structure for that. So let's turn off these. These two pieces we probably want to Cythonize. There's 1 or 2 details of how this index alignment is happening that's a little bit slow, maybe some spurious index alignment that's happening there. But here, always have to do an observed equals true. That's our cumulative volume over time. To figure out the position direction, and to wrap this up, we would just take the sign of this. We need sign from NumPy. And I hope you can see that even though we have these 2 helper functions, 2 helper functions are not very complicated, and yet every one of these analyses are shorter and more direct. And we don't have this awkwardness of just stacking columns on. Well, here, let's get our last piece of this. We'll take the sign here, and then we'll group by the asset, and we'll transform this. We'll get our group, and we'll do our same little group trick here, where we check to see if it's not equal. The reason we use not equal is that'll give us a false if it has not changed, and a true if it has changed, and we do a sum over that. Well, that sum is going to take the true values, 1 values, and just tick it up. So that number will just tick up every time you see a change. Do a cumulative sum here. And now we have, of course, observed equals true. So now we have our position number. And what we probably want to do with this is, because we have that unique identifier, we'll drop date and asset. And now we have a structure we can then group by and index against that starts with, probably we want to name this. So rename, this would be our position number. Now we have a structure that we can group by against in order to figure out what position something belonged to. And we can, of course, group by to get the asset as well. So given this, we would take this result and we'll dot lock this against, actually no, we'll take our prices are just the cash values. Well, the prices are really just the cash values divided by the traded volumes. So that's one other detail we could then figure out. We could align that on, we could take a drop level and drop the asset. To get the prices backed out of this, that's just take your trades and remove its attempt to index line on that, and then take the cash rather, and then divide by the trades. So that just gives you the price. And I think we got to turn this back on. And then here we take this, and you can see those are that. And of course, prices are always positive. So here we take the absolute value of this and then group this by, and we group it by s dot values. And here we'll do a mean. And now we should have our average per position traded price. And of course, this is different than before. This doesn't tell us the one's NAND and one's non-NAND, but this would be the average traded price per position. If we wanted to tie this back to what the original data was, well, here we can do a set index. This is probably going to have to be done in another pipe. Just to get this correct here, we'll take its index and we'll take our original trading data. We'll drop the date and asset level. We'll do a dot lock to get this. This is, I think, that there would be, just have to think about this. This is going to be grouping on our position number. So we actually have to pull this back to the trade number. So since we did the mean here, we're gonna actually need to do two aggregates. Do this. Here we need a mean and a set. Actually, we need to do the set on the here we're going to do this on g.index.get level values. And this is trade. And we can get a set of all the trades that correspond to that position. And then we'd have to back that out. So getting the alignment back takes a little bit of time, but here you can see, this is position number one. This is what the traded average price is, and these are all the corresponding trades that operate on this. Probably we would probably explode this piece. I gotta remember how to name that. And this would be a set axis columns, but I think you get the general idea. This is our price. These are our trades. I'll explode the trades. And then we'd align that back to the original structure to figure out how to get those. Likely, we would want to have, and you can see here, there's these silly inconsistencies of pandas. Sometimes you can say columns equals, other times you have to say axis equals columns. Silly inconsistencies that honestly are not worth worrying too much about, but here you go. This is the trade number, what the average price was, and the position number, and then from that we can easily pull that back into what the actual traded details were. Whatever the case may be, you can see that working through these analyses, where I promise you, I didn't have the solutions written out on my side screen over here. I've done these kind of problems before a number of times, which is why I'm able to talk while I type. But largely, what is distinguishing my ability to use these tools effectively in order to answer these useful questions is not that I have memorized the Pandas API. It is not that the Pandas API is particularly consistent so I can just guess what's there. You can see sometimes I try it one way, it doesn't work, and I try it another way. It's that there's a coherent model behind Pandas that's lurking in the background that really isn't talked about enough. And once you have a good sense of that, the approaches just kind of make sense. You pull them out of your brain, you say, of course, it's an index aligned structured, so I'm going to think in terms of that index, I'm going to think in terms of series objects, and just a little bit of data modeling, and in this case, a non-traditional data modeling, gives us an approach that I think works out significantly better, significantly less noisily, despite being quite distinct from how everybody tends to do this. That takes me to the end of my prepared material. I'd love to hear your thoughts.
Well, that was absolutely astounding. I don't think I've seen someone operate in Pandas as fluently as you do, but I appreciate your explanation of sort of the mental model you have about, how Pandas operates. I wanted to remind everyone there was a link in his presentation at the very beginning. I'm dropping that in the chat now. If you want to sign up for their mailing letter, the newsletter is on there. A few people did have a little issue with putting their email in there. So if you're having an issue, just drop it in the chat too, and I'll dump it in for you. Also, he's going to be speaking tomorrow, starting at 8 a.m. Eastern, 5 a.m. Pacific. And that's going to be going for 5 hours or so. So that's sure to be just as astounding. There's also going to be a recording available.
For that presentation, if you work at a large company, it's very likely you have an O'Reilly or a Safari subscription. One thing I'll note for you is, especially since it's quite early on the West Coast time, if you join the session, you get access to the recording on the O'Reilly platform. So my hint would be, if it's a little bit early, just log in and leave the browser open, and then just come back to the recording once you're fully awake for the day. If you RSVP for the session, but you don't join at all, I don't think they give you access to the recording. That's O'Reilly's rules.
All right, so sign up. I believe you can get a free trial. One of the links on that MailChimp link that I've posted in the chat should allow you to sign up. All right, Daniel asks, what jobs involve using pandas in a professional setting? Also, don't use this code hiring?
So I'll answer both questions. The first question, what jobs use pandas in a professional setting? Well, there's two ways to answer this question. There's what jobs use pandas because that's the most important tool or the most important skill or one of the most important skills, or what jobs could use pandas because it's a helpful skill along the way. The latter question is a little bit surprising. A lot of people that I work with who tell us, oh, we mostly do n-dimensional analysis, we mostly work on surface data or image data, we don't really have to worry about pandas that much. For example, some of your colleagues here work at national labs. It's very common at light sources. People think in terms of images and those kind of data sets, and they say we don't need pandas. But lurking not too far away from the image that they're analyzing is going to be some metadata about that image. Oh yeah, we ran the instrument on these days, and on these days it had a fault. That's time series information. You can analyze it with pandas. Just because you have those kind of problems, does it make it worthwhile to learn pandas? Well, in my view, pandas is actually pretty straightforward to learn if you take the right conceptual approach. And then there's a long tail of just remembering how to spell everything. And so I would argue that columnar data time series problems show up pretty much everywhere. And if you're interested in learning, or if you enjoy learning pandas gives you one more tool to look at these kind of problems where they might show up in your work. And I have yet to find a field or discipline where there isn't some time series data or metadata of some sort somewhere, even for people who swear up and down, all I do all day long is radiation hydrodynamics. I'm always working on simulations, only ever n-dimensional NumPy data. And you ask, well, do your simulation jobs ever fail? Do you ever track how they failed or why they failed? There's some metadata there. Could be columnar metadata. Now, the second part of that question, or the other approach for answering that question, is what jobs use pandas as one of the premier tools? Obviously, you can see the time series analysis here is from a financial perspective. We've worked with a couple of different hedge funds and risk management groups, and pandas is a very popular tool for these kind of portfolio analysis or strategy analysis, or even any kind of analysis of this time series data. Likely for any sort of high frequency or very high fidelity or tick level or very large data structure analysis in the forms that I've done today, pandas is fine, but you're going to see some performance limitations. You probably wouldn't want to write a high frequency trading backtester on top of pandas. It probably wouldn't be fast enough. But you can think that these kind of financial or accounting level analyses are very common in that field. Beyond that, one project that we worked on for quite a few years that was not as different from the financial projects that we work on, as you might expect, was we were in a very, very large data center, one of the largest data centers in the world, and somebody had put on all of the networking equipment that they had an out-of-band device that would just report signals every tick. You know, how much memory the device had, how much CPU, whether the device was RMA'd, whether it was up or down, whether it had dropped packets, whether it had link flaps. And somebody comes around and asks, you know, how can I run my data center more effectively? Time series data. Oh, did you know when the passively cooled data center and then there's wildfires in California and they have to shut the windows and then the heat goes up, you're getting a lot of network issues? Here's some time series data analysis backed by pandas. Any sort of columnar data analysis that is done on tail end analytical data, data that's already been captured, that's not done on streaming data or similar, that's done on data that fits into memory, that can be benefited by an index approach, probably can be analyzed effectively in pandas. If not in pandas, then in polars or DuckDB. And then finally, we are in fact hiring for junior instructors right now. And we're hiring aligned with another effort that my colleague Cameron, I think a month or 2 months ago, came to speak about, you know, some efforts related to a NASA grant that we have.
Awesome. Surav wonders, are you going to be joining PyCon India this year?
So I believe that I have been asked to keynote PyCon India this year. And I think the only thing that's missing is I have to be at PyData Amsterdam 2 days prior. So I think I'm just dragging my feet on finalizing my air travel. So I go to PyData Amsterdam and then fly down to PyCon India, which is in Bangalore. And 5 days later, I'm keynoting at PyCon Japan. So I have to figure out how to manage all that travel.
All right. It looks like your headshot is already on the website. So they're pushing.
I think I'm already confirmed. It's just really just a matter of figuring out how to get there.
It sounds like columnar data could probably crunch through that.
Well, you know, that's the thing, you know, for airline ticket prices, I don't need pandas to tell them they're going to rip me off like nobody's business.
Of course.
Kind
Robert,
of a random question, if you have time. So in terms of like getting into data science, I hear about Power BI, right, as like one of the tools to use. And how does pandas compare to some of these non-Python tools, right? It's to me, it seems like Python is kind of a closed universe for kind of scientific data, and I guess in terms of portfolio analysis, you have that for non-high-speed financial analysis, right? But how does it compare to, say, something like Power BI?
I have not used Power BI much, so I can't comment directly on it, other than from what I've seen, I wouldn't touch it with a 50-foot pole. And the reason for that is maybe good reasons and bad reasons. Maybe, and you can kind of align what you think are good reasons or bad reasons. It is absolutely, undeniably the case, even in comparison to tools like R, that Python and pandas are very mechanical tools. Like when you see me write that pandas code, it's clearly that I'm doing these mechanical steps to transform, whereas in R, oftentimes you're almost declaratively saying what you want the result to look like. Definitely in tools like Excel, it doesn't feel like programming. And if you don't have that programming bent to you, if thinking in terms of mechanical steps and things like variable assignments and all of those other mechanics isn't your first intuition, I can easily see where something like Power BI or Excel going to be much more comfortable for you. Whether it's a good reason or a bad reason, I know that I come from the programming perspective, and anytime I see a tool, I'm thinking, well, how can I automate on top of this tool? And that's why I wouldn't touch Power BI. Anything where I look at that, I'm like, I'm going to be sitting here and clicking things all day long.
Right.
I don't want to go near. Right? I want to write code that does the clicking for me. And if you're ready for that, if you think in those terms, that's where Python and pandas are materially better tools.
So something like Power BI is really for non-programmers.
I think so. I think that it's hard to say that because you could also say that SQL originally was a tool created for non-programmers. This is the thing I think that's so wild. When you go back and you read old magazine articles or old publications about SQL from even like the 80s or the early 90s,
Mhm.
like the ideal SQL user is some business analyst with an MBA. And then these days, we assume, well, you have a computer science degree. Is that good enough to write SQL? I feel like a lot of the work and the inherent complexity of the problems that are solved build some complexity into the work. So I couldn't say that Power BI is for non-programmers. I'm sure that there's people out there who are doing some enormously sophisticated stuff. And you do it for long enough, it just becomes a complex thing unto itself. And you need to have that expertise. I'm sure there's somebody out there in the world who calls themselves a Power BI expert, and they genuinely, legitimately know more about this tool and have studied it and learned the intricacies
Right.
more than anybody else. I think that the style with which you create, manage, and think about the artifacts of work with Power BI does not match the way we think about this in programming languages like Python. In Python, the moment you solve the problem once, you're thinking, how do I write a library to solve it every other time? Hence, I don't think that's the first intuition with these other tools.
So for things like portfolio analysis, there had to be a time when Python was foreign to the people and these hedge funds, and someone had to kind of introduce them to the idea of using Python for this.
I think largely what the shift would have been from other programming languages to Python. So Q, KDB, R, MATLAB, C, C++, Java, or whatever to Python. Not so much. I would be hesitant to think that some of these analyses would have originally been done in Excel. I suspect they wouldn't have been done in Excel or similar tools. They would have been done in another programming language. That said, the Excel to Python or the Excel to pandas pipeline, we know that exists. We know that's a real thing. And we know there's people who start with their data in Excel. In fact, I was on a client call just today where they told us about an agent model that they were working on that was written as an Excel spreadsheet, was impossible for them to maintain. And they're like, we got to turn this into an actual script. We got to turn this into actual code that's something you put on GitHub. That's a real thing. And I'll tell you my controversial Excel opinion. Excel is, number one, probably one of the most useful actual tools for doing work that has ever been invented. Despite all the complaints and all of the problems, so much actual real work has been done in Excel to solve real problems. It's worth something. I think the same thing about SQL. SQL is very imperfect, but the amount of real, genuine value that it's generated. Same thing with shell scripts. People complain about shell scripts all the time. You know how much real work we've done in shell scripts? It's not a great tool, but it's brought so much to the world. Second, I think that as a UI, Excel is actually fantastic. The idea of a giant grid that you can scroll around and you can just kind of go off to the side and do little scratch work. Every time somebody tries to replace Excel in one form or the other, I think what they get wrong is the density. All the web-based grid tools, they're not as dense. When you look at a trader, they'll have a 30-inch monitor. They'll have Excel zoomed out, and they'll have so much data on the screen with such high density. And then they'll go over to a column over there, do a little bit of ad hoc work, say, does that look right? Kind of go back to the data. And that use case, the speed, the effortlessness, the ability to do ad hoc work, Excel is great at that. As a computational or calculation tool, Excel is fine. It's definitely better than Google Sheets, which is pretty bad. But it doesn't take a lot before Excel really shows its limits. Yeah. One canonical example that we use to illustrate the limits of Excel is a scenario analysis problem. Let's say we're analyzing a business and how a business might perform over the next year. And there's different scenarios for what could happen. Like, so-and-so is elected and, or such and such bill passes, or such and such other industry has something, or such and such other thing. There's all these scenarios that occur. The way you would do that in Excel is you'd have one sheet for each scenario that you want to create. And you'd copy and paste the structure of the table from sheet to sheet to sheet. And you change a couple of small details here, maybe add in a little more things, and you give it to somebody. Well, you have to physically and manually create each one of those sheets and maintain them in tandem. And so if somebody says, look, there are 5 events that we want to track, and we want to see what the power set of those events are. So not does event A happen, or event B, or event C, or event D, or event E, but any possible way they could be combined. So-and-so is elected president, and such and such company, country has an earthquake, and something else happens, but not something else. It's very difficult to do in Excel because you run out of copy and paste. You run out of spreadsheets you create. In Python, it's almost trivial to do. This is just itertools.combinations in a comprehension with a itertools.chain and a little bit of pandas code. Looping as that core concept in Python is so trivial, we don't even think about how useful it is. And when you think about scenario analysis, it's really about construct all the scenarios and then loop and just do something for all of those. Python programmers don't even think twice about that, but Excel users, they got to manually create each one of those sheets. Excel is actually a very poor tool for that. Python is a remarkably better tool, especially when somebody says, oh, you know what, scenario D, that's never going to happen. Strike that. Python, you just comment out one line. In Excel, you're just,
So one potential client we had is a manufacturing company, right? And so they had like a product database, and like only one person actually interacted with the product database. It's a special customized data, and to get the data.
I think we lost a couple of the details from Robert.
Yeah, that or he's deep in the inference. Yeah, it seems like we've lost him on that one. All right, well, it's past midnight and I know you need to get going. Oh, Robert, it appears you dropped. We're just talking about the data with this manufacturing thing.
Can people hear me right now?
Yes.
Yes.
Okay, so I'll quickly repeat it. There's such a thing as a product manufacturing database, right? It's a custom thing. And so the way Excel comes into this is there was only one person who had access to this product manufacturing database, right? But for everybody else to have access to the information, they just dumped it to Excel, right? Because everybody has access to Excel. And then obviously the power tool is to use pandas, but to get pandas installed on the employees' computers, that means getting a lot of buy-in, right? So that's where these less efficient tools like Excel, I think, keep popping up.
One thing I like to do is create Excel spreadsheets, high fidelity Excel spreadsheets using Excel WT, and use that as the interaction tool. So for example, if you have some sort of, data tool that's like a web-based tool, allow people to upload or download Excel spreadsheets. Let them use Excel as the UI to set things up, but do all the actual computational work separately in pandas. It's so much easier to do it in pandas.
Yep.
But let's not throw away what is a fantastic UI that has extremely high data density, and it's just so easy for people to just intuitively use.
Yeah, that's a great idea.
Actually, did you ask your question about PySpark? You're muted.
No, yeah. So, no, not that. I wanted to ask you something else. So I totally agree with James about like, starting with Excel and then migrating to something like pandas because, at least you can start prototyping. So that's something I did for the NASA TOPS project. So, we got some data into Excel, just saw like what we can do based on our hypothesis, like a null hypothesis and alternate hypothesis, just like came to a conclusion and then let's reproduce this using a script so that we can put it on the notebook and like, show everything out there. So the question that I wanted to ask you was like how would you like choose what you want to do between group by or like pivot table? Because I mean, sure, like they do have their own importances, but I kind of got around using group by. Instead of using group by, I did the same thing using pivot table, but will it be more better if I use like the chaining mechanism of pandas with group by rather than just like doing very sophisticated work with pivot tables? So that was one thing I wanted to understand because that was something that threw me off when I was doing it during
Are
that
you referring
project.
to the Excel pivot table or the pandas pivot table?
I mean, I tried. I didn't know, to be honest, like if Excel has something like group by. I know like they have pivot table. So I did in Excel pivot table. Did Excel pivot table, and I was trying to do the same thing in pandas group by.
So
And
pandas has a pivot table as well. It's just
yes,
that it's difficult for people to understand what the arguments mean. If you want to think about what a pivot table, at least a pandas pivot table is, it's just a group by unstack.
exactly. I had to do like this, and then I have to unstack and drop some levels so that it looks proper. So in that case, it would be much better if I use group by default, right?
I have to dig around in my notes. If I remember, at one point the code path for pivot table was effectively the same as the group by unstack approach. The only distinction that I was going to make was when you unstack, you take something that you consider to be homogeneous and you break it into multiple different data sets with some particular alignment. You have the ability to introduce nans because it might not be fully built out. You might have some gaps. Pivot table has a fill value, and unstack also has a fill value. But in older versions of pandas, if you had integer data and you started to fill in those values with say 0 values, it would still go through floating point data and then back to integer data. So you could have loss of information in the in64 to float 64 and then back to in64 conversion. And if I remember correctly, at one point in time, pivot table, I think, did not incur that loss of information, or there was maybe a loss of the capital I in 64D type when you went through pivot table, but not in group by unstack. I think that was the only distinction I found, but I don't quite remember, and it's probably out of date. So my general guidance would be pivot table, use it if you get the API, group by unstack, use it if that's easier. What's more important is, one, understand the group by modalities. There's actually 3 group by operations, and if you're an SQL user, the 3 pandas group by operations, only one of them looks like an SQL group by, the other one looks like a SQL window function, and the third one is not actually present in SQL. So group by in pandas is actually 3 different things: ag, transform, and apply, where almost no tool with a group by has an apply equivalent. Apply basically can do anything. Learn and understand those. Second, understand what the transformation structures do, or the transformation operations do. Melt and pivot in pandas are generally strictly not necessary. The real idea is stack and unstack. And understand what is stack and unstack really actually doing beyond just moving levels of my column multi-index to my row multi-index. There's a conceptual weight behind this, or conceptual semantic meaning behind this. Those 2 pieces together give you what you need. Once you understand what all the group by modalities do, and you understand why and how to transform the data, then it's not uncommon for your analysis for you to think in terms of what that output table looks like. Think in terms of what that Excel pivot table would look like, see what the original data looks like, and be able to say, oh, I'm at A, I want to get to F, I go through B, then C, then D, then E, and then F. You can kind of trace those. And this is largely how a lot of analyses I do. I think, what does the output look like? What does the input look like? And then I have a sense for what do each of the steps along the way get me. That would be my general advice, not knowing the details of your problem.
Thank you. Thank you so much.
You're welcome.
Awesome. Well, we've gone a little over the time we had allotted. James, I just want to say once again, thanks so much for your time. Amazing presentation. And I wish you all the best tomorrow. And
Thank you for inviting me.
of course, thanks everyone. We will see you again in a month or tomorrow. Take it easy.
Thank you, James. It's an awesome presentation. Yeah.
Bye.